Okay, so where we stopped, what is the last thing we covered? Okay, now we're talking about AC analysis. That is what we are talking. So let me summarize what we do in AC analysis. So you could have the circuit in this format, in the time domain format, where you will have this as a cosine or as a sine function. So let's say it's a cosine, a cosine omega t plus theta. Then you will have R1 connected, maybe L1, maybe R2, maybe there is another L2, maybe there is C1 and L3, something like this. And you are asked to find, for example, what is the current here, I of t. This is the question. So this is, we call it the time domain representations. As such, this circuit, you need to use differential equations, and having many L's and C's, then you will have a very, very complicated number of differential equations. Then you have to solve, instead of solving algebraic equations, you need to solve simultaneous differential equations, which is much, much harder. So we said, okay, for AC analysis, specifically for AC analysis, we can change the time domain into the frequency domain, and sometimes, or we call it the phasors, either this or that. So what we do, we redraw the same circuit. We don't touch the circuit. So the circuit is exactly the same. No change here in the configuration of the circuit. But instead of working in the time domain, we will convert this into phasor. So for the voltage, it will be just the magnitude and the angle. It is a vector in polar format with this is the magnitude and this is the angle. The resistors, nothing happened to them. But the inductors, this becomes J omega L1, J omega L2, J omega L3, and omega, I got it from the source. This is the omega that we use it here. So the omega will dictate the impedances of the circuit, and this is minus J over omega C1. Now, once we have the circuit in that format, then we will use, for example, I can use nodal analysis. This will be V1, this will be V2. This is my reference. Find V1 and V2. Your current I here is nothing but your V2 divided by minus J over omega C1. Once you know I, you can convert it back to the time domain. So this is the procedure. However, sometimes the circuit will be given in that format directly. So you don't need to do this conversion. So this, sometimes you need to do it. Sometimes you don't have to do it if the circuit was already given to you in the phasor or in the frequency representation. Okay, so let's see this circuit. It says here, draw a phasor diagram illustrating all voltages and currents. So we want to find the phasor diagram, and we have seen this phasor diagram before. And to find the phasor diagram, you need to find the phasor quantities, or the voltages and the currents. So we have here this main current I, we have I1, we have I2, and we have V. So these are the four quantities that we want to draw. Now you notice here that the values in the circuit are already given to you in the frequency representation or in the phasor representation. So the current, this is a current source. We have a magnitude and an angle. R, nothing happened to it as usual. And the capacitor is minus minus J4, which is derived from minus J over omega C. In this question, omega for us is not known, and it will not be known for us because it's not given in this question, and we don't need it because the circuit is already has been given to us in the frequency representation. So this, which is usually minus j over omega c, I don't need to calculate it. So I don't need omega here. Okay. Now we have a current source. It sees two branches in parallel. So obviously, one way to solve this is current division. Current division is an easy way. Of course, you can do different techniques. There is no, as I mentioned before, in the final, I will not dictate the technique that you'd like to use. People, they have different tastes, they have different experience, they like this more than that. So and also it depends on the person and it depends on the circuit. Sometimes it's much easier to deal with certain circuit, or sorry, with certain technique for this. So this one, when you have a current source and two parallel branches, definitely current division is one of the best to deal with this. Okay, so what is I1 here? Your I1 is equal to I, the main current, which is 4 angle of 45, times the other impedance, which is minus J4, divided by the summation of the two, which is 2 minus J4. Now I have here a multiplication. I multiply a polar with rectangular, so I cannot do this. And since we have division as well, so it's better to have everything into polar format. So this is equal to 4 angle of 45 times. Now here comes the software I showed to you. You can use that. So minus J4, this is nothing but 4 angle of minus 90. And 2 minus J4, this is nothing but 4.47. And the angle will be minus 63.44. As I said, 2 digit after the decimal is more than enough. Even 1 digit will be sufficient. So here we multiply the 4 times the 4, then divided by 4.47, and then I will do addition or subtraction. So this is 45 plus minus 90 minus 63.44, and when we do this, you will find that your I1 is equal to 3.58, and the angle will equal to 18.44. Okay, so now we are done with this. With I1, we want to find I2. How to find I2? I2 do the same thing, current division. Or you can say that I2 is equal to I minus I1 KCL. However, it's better to use this because we already converted this into polar format. Otherwise, here, when you do the subtraction, you have to convert everything to rectangular format. So you have to convert this to rectangular. So that would be easier or faster, if you may say. So this will be equal to 4 angle of 45 times the other impedance, which is the 2, divided by 2 minus J4, which we know this is 4 angle of 45 times 2 divided by, this will be the same thing here, 4.47 angle of minus 63.44. And when we do this, you will find that this current I2 is equal to 1.79 with an angle of 108.44. So this is your I2. This is your I1. We need to find V. So your V is very straightforward. Your V is equal to 2 times I1, or is equal to minus J4 times I2, because V, what is V? Is the voltage between these two nodes. So it is the voltage across the capacitor or across the resistance. So this is easier because there's no the multiplication by a scalar only. So it's 2 times 3.58 angle of 18.44, and this is equal to 7.15 or 16. angle, the same angle, nothing will change in the angle. Okay, so we are done with this. Now we found V, we found I1, we found I2, and we found I. So everything we want to calculate has been calculated. Now we need to draw the phasor diagram. So let's draw the phasor diagram, and we'll use here different color to make it uh, easy for you to visualize. So let's start with the black to draw the axes. Okay, so we'll draw the y and the x axis. Okay, so this is the real and this is the imaginary. Okay, now we'll start with the currents and then we'll find the voltage. So we'll start with the main current I. I is equal to 4 angle of 45. So the angle is with respect to the positive x-axis always. So I is 4 angle of 45, so it comes here. So this is angle 45. The magnitude here is 4. And this is your I with the magnitude 4. This can be like relative speaking. You don't have to, even in the exam, if I ask you something like this, you don't have to show it to scale, just relatively. Okay, your I1 is 3.58, but the angle is less, 18.44. Let me draw I1 now. Let me change the color as well. So your I1 has a similar magnitude. So the magnitude wise will be like similar to each other. So this is your I1 with the angle is equal to 18.44. And this is your I1 with the magnitude equal to 3.58. Then after that, we have I2, which has much less current. However, it has a different angle or much larger angle. So this will be something like this. So the angle here is 108, 108. And this is your I2 with a magnitude 1.79. As you can see here, it's just sort of relatively speaking. Now your V is basically at the same direction as I2, but double the size. So we just extend this. So this is the same angle. This is your V with a magnitude of 7.116. So with this, we constructed what we call the phasor diagram, okay, which is the vectors basically, because as I said, now we are dealing with vectors, so that's just the vectors. Here are all the calculations. Here you have it here in details. Let's have this question as well. It says here, find the steady state current. So here we have one current, I of t. So we want to find I of t. Phasor voltages. So we want to find the phasor voltages. So basically we have here uh, 4 voltages. We have V supply or VG here. We have VR, we have VL, and we have VC. And construct a phasor diagram. So we want to find the phasor diagram as well for this. Now this circuit, as you can clearly see, it's not given in the phasor, it's given in the time domain. So we need to change this. How to change this? Okay, very straightforward. The voltage is 100 cosine, so it's not sine. If it's a sine, you subtract minus 90. So it's a cosine, so it's 100, and the angle is 30. But here you can, now we need to extract omega. So from this, your omega is equal to 500 radian per second. So this is your omega. So this is 100 ohm. This is J omega L, which is equal to J times 500 times 0.3, which is equal to J 150. Okay, so this is very important. Now, you should not, and this is, as I mentioned before, this is one of the common mistakes. The student will just keep this as zero point 0.3, this as 40 microfarad, and this 100 ohm, and then start to apply KCL and KVL. You cannot do this. You have to change everything into ohms. This is ohms, this is ohm, this is has to be also ohm, which is minus J over omega c, which equal to minus J divided by 500 times 40 times 10 to minus 6. And if you do the calculation, this is equal to minus J50. So now my circuit is ready. I will have this circuit with all the quantities. I will have the supply, 100 angle of 30. I have VR. I have, sorry, the R, 100 ohm. And we have the 150J and the minus J50 for the VC. Now we have also VR, VL, and VC identified. And here, go back now. Let's go back and refresh our memory about the circuit analysis. Remember that we'll assume that the current is going, okay, uh, leaving the positive terminal, okay, and plus minus, and plus minus. And now we can apply KVL, okay? So apply KVL, or you can, yeah, apply KVL here, KVL. So we have the voltage here is VR, or 100 times I. So this is 100 times I, plus the voltage here is J50, J150 times I, minus J50 times I, equal to 100 angle of 30. Okay, excellent. So I can take I as a common factor here. So your I is equal to 100. J150 minus J150, this is equal to plus J100, equal to 100 angle of 30. So from this, remember, the first thing we want to find is the current. From this, we can say that the I is equal to 100 angle of 30 divided by 100 plus J 100. We can simplify a little bit here. So this becomes 100 angle of 30 divided by, I will take this 100 as a common factor, 1 plus J. So this will cancel. So your I will equal to 1 angle of 30 divided by 1 plus J. Now here I'm doing division, so I'm dividing a polar with a rectangular, okay? I cannot do this. Why I cannot do this? Because very straightforward, because I cannot divide polar with rectangle. So I have to have everything into polar. So this is 1 angle of 30 divided by 1 plus J, which is will be, I will convert this into polar. So this will become equal to 1.41 angle of 45. So this will give me 0.707 angle of minus 50. So this is your I as a phasor. Okay. Now we want to find I of t, because this is what we want to find originally, I of t, the steady state current, I of t. So your I of t, so it's very straightforward, your I of t now, we can easily convert this. So this is the magnitude, the 0.707 with the cosine of omega, which is 500t. This doesn't change. Omega stays the same. Any quantity you want to find with this circuit, it will have the same omega, because omega doesn't change. We have only one omega in the circuit, and this is minus 15. So this is your I of t. Okay. Now, are we done? Not yet. We need to find the phasor voltages. not the steady state voltages or the time domain representation. We need to find only the phasor voltages. Now here this is something very interesting I want to say here about the circuit. Now this circuit is composed of a resistance, an inductor, and a capacitor. So we have the inductor and we have the capacitor. But clearly here we can say that the dominant part is the inductor. So at the end of the day, this we found that the total impedance here, when we have them in series, they are 100 plus J100. So if I want to draw this, it will be just a resistance 100 ohm and an inductor with a value of J100. Basically, this circuit represents this value, real part and the imaginary. And there is no capacitor. Why? Because the capacitor and the inductor, they are 180-degree between each other. So one cancel the other. So in the circuits here, we call, is this is a common question. Is this is a capacitive circuit or an inductive circuit? What does this mean? Capacitive circuit means that the capacitor component is the dominant part. Inductive circuit is the opposite, is the inductor is the dominant part. Now how I can tell is looking to the sign here. If the sign is positive, then it means that the inductive part was the dominant part, because the positive was more than the negative, then they will cancel, uh, as if the capacitive doesn't exist at all after reducing a little bit of the inductor. If this sign was minus, then this whole overall circuit, we call it is a capacitive circuit, because the capacitive component is dominant in this circuit. So this is something very important to notice. Now let's continue here. So here it's very straightforward. Your VR, which is the voltage across here. Now VR, VL, and VC is nothing but the current I times the impedance, Ohm's law. So VR is nothing but the 100 ohm times I. VL is nothing but the J150 times I. VC is nothing but the I times the minus J50. So here VR, R times I. R itself is 100, so 100 times the current. Now we multiply everything in phasor. Now since this is a scalar multiplication with a vector, we just multiply the magnitude. Nothing will happen to the angle, stays the same. Now VL is equal to J omega L times the current. Now this J50 is nothing but 150 angle of 90. So multiply the 150 times the 0.707, we get 106.1, and then the 90 minus 15, this is the 75. Come here for VC, it is minus J1 over omega C, which is minus J50 times the current. Now this is nothing but 50 angle of minus 90. So the 50 times the 0.707, we get this. And then we have the minus 90, the minus 15 is equal to minus 10105. Now we are set to find what? To find our phasor diagrams. Okay, so basically here, I don't need to draw it with different colors. Now you are getting the idea. So start with our basic voltage, the main voltage, which is Vs, the supply voltage, which is 100 angle of 30. So this is becomes a vector here with angle of 30. This is your Vs vector. Then you have your VR. VR is nothing but is the 70.07 here with an angle of minus 15. This is your VR. And it's the same for I. I will be something here. This is your I, which is because we know that I and VR, or the voltage across the resistance, they are actually in phase. Then we have VL, which is 106 with an angle of 75, so something here bigger. I suggest you, when if you do this yourself, you do it with different colors. This is will be better for the TA to mark your exam. This is your VL. And finally, your VC. Now, your VC will be 100-degree phase shift from this. So it is from VL. So this is your V. This is your VC. And the angle, its angle here, it is minus 10105. So this is your VC, VR, VS, and VL. So this is the phasor diagram that you need to construct. Okay, now there are few examples, but because today we have the first day for the course evaluation, I will stop the course here and I will give you the rest of the class to go and do the evaluation. And please, this is very important for me, myself. I'm developing this course since 2018. And with the help of your feedback, I am changing the course actually. Every year I'm adapting to the comments. I will see what are the things, because this course is, if you may say, it's a custom made. It's basically done for only civil engineers. It's not done for anyone. Mechanical, they have different version. Electrical, they have different version, and so on and so forth. So your feedback is very important for me. On the course and on the lab, I really appreciate that. So please utilize the rest of the class to do the evaluation. Okay, so see you tomorrow for more examples, and I will prepare some more bonus points tomorrow. So please come prepared. I will be throwing some bonus marks. Okay, thank you very much, and see you tomorrow.